The p-block elements. The p-block lies on the extreme right hand side of the modern periodic table. You know that it contains 6 groups and is having almost the 7 periods. It's the most complex type of the block we are having in the modern periodic table. The reason being that because it not only contains metals and non-metals, but it also contains metalloids. So what we find is that the properties of the elements changes drastically as we move from top to bottom or from left to right, and that is why we find that the properties are changing in such a big way that the initial elements though are non-metals, then we have metalloids, and then in the end we are having what in the 6th or the 7th periods we are having metals. That's why this particular block is very interesting, and it involves a very complex chemistry of the different elements which are present in them. Those elements whose last electron enters the p-block subshell or suborbit, they are actually placed in the p block. Now the general electronic configuration of the p block elements is ns2 np 1 to 6, because the p will be having 1 to 6 electrons. Let me give you a brief introduction of the elements of the p block. It starts from group 13th, then we have 14th, 15th, 16th, 17th, and in the end we have 18th. The 13th is called boron family. It's having boron, aluminium, gallium, indium, and thallium. The group 14 is called carbon family. It's having carbon, silicon, germanium, tin, and we have lead. Group 15 is having what? Nitrogen, phosphorus, arsenic, antimony, and bismuth. Now group 16 is having oxygen, sulfur, selenium, tellurium, and polonium. Group 17 is having fluorine, chlorine, bromine, iodine, and astatine, whereas the group 18 is having, of course, helium, neon, argon, krypton, xenon, and radon. So this is what we have the p block. Now we need to know this, that the group 15 are called, so group 15 elements are also called nicogens, because they have nicogen, which means the elements which produces poisonous gases. So they all, because except ammonia, all of the hydrides of all of these elements are highly poisonous gases. Whereas group 16 elements are also called chalcogens, ore forming. Chalco means ore, jan means forming. So because they all are the ones which constitute the majority of the ores. Group 17 elements are called halogens. Halogen means salt forming, because they are the ones which are mainly responsible for the salts formation. And in the end we have noble gases or inert gases, because they are the least reactive elements we are having exist in the monatomic state. So this is what we have. Now what is most interesting is that this boron, though it is having a non-metallic nature, we call it a metalloid. Then rest of these are metals. In group 14, what we find is carbon is a non-metal, whereas silicon and germanium are regarded as metalloid. Tin and lead are metal. In group 15, nitrogen, phosphorus are non-metals. Arsenic, antimony are regarded as metalloid. Whereas in group 16, the polonium is, though it is radioactive, we don't study this in detail much, but it is metalloid. And that is how we find is that this is what are the non-metals we have actually in the list or in the block. These circled one are your metalloids, and left out one on the bottom sides are the metals. So what we find is drastically the properties changes in these elements. Though in our syllabus, in our school the CBSE system, or in class 11, we are having only 13th and 14th group in the system, and the 15, 16, 17, and 18 you will be doing later on in your class 12th. But yes, we have to know at least in general that what makes these elements more interesting. Now what is after this introduction, what we need to know before moving ahead is this, that we know that they are called representative elements. The first element of the p-block element, p-block groups, they behave very differently from the rest of the elements. Like I'm talking about particularly carbon. Well, let's start it from boron, carbon, nitrogen, oxygen, fluorine. except especially these 5, they behave very, very differently from the rest of the other group members. The reason is very small size. The very small size is due to the poor screening of the 2p electrons, high nuclear charge, obviously because the nuclear charge or the charge density is very high. As a result, high ionization enthalpies, and as a result high electron negativity. And what makes them that because of these things they have very high polarizing power, and that's why their compounds are covalent in nature. And in the end it is the absence of d orbitals. Now, due to these absence of d orbitals, what we find is they won't be able to extend their octet. They can maximum have 4 pair of electrons, and they cannot go beyond that, and as a result we find that there is a lot of problems in this. Now, as a result of these effects, what we find is that these boron, carbon, nitrogen, oxygen, fluorine, they all forms p-pi bonds, because due to their small size, when they come very close to each other to form a normal sigma bond, their p orbitals also get sideway overlap and they form pi bonds. But what we find in the other case is that the rest of the elements, the others forms d pi p pi bond in place of the p pi p pi bond, because they have d orbitals. Another interesting thing, as I have told you, that since they if we take nitrogen forms NCl3, whereas phosphorus of the same group is able to form what? PCl5. Nitrogen is not able to extend its octet because it's not having d orbital, but yes, phosphorus, due to the presence of d orbitals, is able to extend its octet. That's why it even forms pentachloride or pentahalide. Another interesting thing, if they are able to form complexes, they won't be able to go beyond 4. Like if I say we need to know this, even this one, it can form NCl4 minus, or it can go up to the maximum of this. They cannot go beyond this usually. Or if we are having an example of boron, we need to know this boron goes BOH 4 minus, but what we find is yes, aluminium can go up to this boron, aluminium OH 6 3 minus. So there what we find is the difference comes is that they get usually sp3 hybridized, they acquire tetrahedral geometry, whereas the other group elements, they usually acquires octahedral or with a geometry with a coordination number 6 or even 8. So this is what makes these elements very more interesting, and this block very interesting. Now let us start with the group 13 elements, which is called boron family, because of the first element boron of this group. Now the group includes boron, aluminium, gallium, indium and thallium. Now the boron, we need to know this, boron exists in the form of borax, which is Na2 B4 O7 10H2. We'll be doing it later on in the same within this chapter. It also exists in the form of carnite, which is again is Na2 B4 O7 4H2O. So these are and it also exists in the form of orthoboric acid, which is BOH thrice. So these are its main forms in which it exists in the nature. Let us talk about now aluminium. Aluminium, we all know bauxite is its major ore, which is Al2O3 2H2O, and it also exists in the form of cryolite, which is actually is Na3AlF6, which is the halide ore of the aluminium. The gallium, indium, thallium, though all of these exist, but they are found in very, very less abundance, but the percentage abundance is not much. Aluminium is the third most element on the Earth's crust after the silicon and oxygen, and that makes it aluminium very easily available all around us. Now let us do their physical and chemical properties first. Let us discuss their ionization. First let us discuss their electronic configuration. Their electronic configuration is Ns2Np1 of group 13. That makes them to have what? 3 valence electrons, and that's why they all are placed in 13th group, because 13 minus 10 is going to give us the number of valence electrons they will be having. So that's make them very interesting. Then let us discuss their atomic size. Atomic size, whenever we find that atomic size increases down the group, but yes, we have a very different behavior in this. The different behavior is of gallium. What we find is the radius of aluminium when compared with radius of gallium, what we find radius of aluminium is greater than the radius of gallium, and gallium is smaller than aluminium. Though we normally know that as we move down, the atomic size increases, but here the atomic size is decreasing. It is smaller, gallium is smaller. The reason is because we know that before gallium we are filling what, 3D, and 3D is the first time that the D comes in the form of 3D. It gets very poorly screened, and D itself is having a very poor screening effect on the electrons which lies afterwards after the D. That's why what we find is that the NS2 and NP, if we are talking about particularly gallium, it will be 4s2 and 4p1. So what happens is these electrons which comes after 3D gets very poorly screened, and that's why they come directly under the influence of the nucleus, or the defective nuclear charge on these is very, very high, and that makes gallium to shrink in size. And because of the poor screening of the NS2 and NP electrons of the gallium, the size of the gallium is smaller than aluminium. So that is what. And don't think that this is the only, though this effect we doesn't find continuing in the group 14 also. We don't find that we are having silicon and germanium. Germanium is not smaller than silicon. The main reason is because these two unpaired electrons in the p makes, due to their interelectronic repulsions, compensates this effect. But yes, the effect continues of the poor screening of the inner NS2 NP electrons, and that is why what we find is in chemistry of the p block that this whole p block elements belonging to the 4th period, what we find is their behavior is found to be very much different, and that's why this is called middle row anomaly, which is there and which starts from basically the gallium only. So this is the unusual thing we have. Else we find that the size is increasing. Again, it starts increasing from indium to thallium. Thallium also is not very large in size in comparison to what we usually can think about it, because again there is a very poor screening of the its NS2 NP electrons because of the lanthanoid contraction, or because of the poor screening effects of the inner F and the D orbital. So that's the usual behavior we have in their atomic sizes. Now let us discuss the ionization enthalpies of the boron family. The ionization enthalpy, it decreases down the group, obviously because the atomic size increases. But what we find is ionization enthalpy of aluminium when compared with first ionization enthalpy of gallium, we find that gallium's first ionization enthalpy is higher. The reason is because the radius of aluminium and radius of gallium, if we compare, the radius of gallium is smaller than radius of aluminium. That makes it to have higher ionization enthalpy than the aluminium one. That's the only thing which we find. Otherwise, it keep on decreasing down the group, and what we find is it becomes more and more higher and smaller in nature. But again, what we find the best other thing which makes it very different is that in case of indium and thallium, the second and third ionization enthalpies of thallium are high. Now the reason is because of the poor screening effect of screening of the NS2 electrons of the thallium, and or we can say it is because of the poor screening effect of the F and the D, inner F and inner D electrons, because of which the second and third ionization enthalpies of thallium are very, very high, much higher than what we find in case of indium. They are higher, and that is why thallium is more stable in +1 oxidation state and indium is more stable in +3 oxidation state. Now let us discuss the next property, which is the electronegativity. See, See, they are as such, most of them are metals. They are not electronegative in nature, but yes, they are as per when the size is compared or when we are comparing them with the alkaline earth metals, they are very electronegative in nature. And electronegativity, it decreases down the group, and it decreases continuously from boron to thallium. It decreases down the group. So now let us discuss their physical properties. See, all of these, let's start with boron. Boron is more or less, we regard it to be a non-metallic in nature, but it's very hard, it's very strong, tough substance. Borides are very, very strong substances, we all know, and they're a strong and abrasive material, and it's having a very, very high melting point. Now, then other than this, aluminium, gallium, indium and thallium, all of these are soft metals. And we know that aluminium, that is what makes it aluminium different. Otherwise, it's very, very useful. And nowadays, we use it very commonly for the construction purposes. But being a soft metal, that is why it's not very much recommended for using it to be a very hard metal. Wherever we need hardness. Gallium, in spite of being smaller than aluminium, is having a very, very low melting point. In summers, it is almost in liquid state. And but its boiling point is very, very high. That's why it is very commonly used to find out the boiling points of the other substances. Indium, thallium are having on an average a very low melting point. They are soft metals. Density also, what we find is they are differently changing down the group, and these are the certain special physical properties of the boron family. Now let us discuss their chemical properties. And in the first, we have oxidation state and their other chemical reactivities. In the oxidation state, we know that their general configuration is NS2NP1. What we find is they show a very different phenomena, unique phenomena called inert pair effect, which is actually is a consequence of the poor screening of the NS2 electrons specifically by almost the inner F or D electrons. Now, due to this poor screening of the NS2 electrons, their nuclear charge experienced by these NS2 electrons is very, very high, and as a result, their ionization enthalpy, the second and third ionization enthalpy, or the energy required to take out these electrons, becomes very, very high. And that is why what we find is, as we move down the group, the stability of the higher oxidation state decreases and the stability of the lower oxidation state increases. Let us discuss boron, aluminium, gallium, indium and thallium. We know that they can show +1, +3 oxidation state, and that will be their the best state, because to attain the noble gas configuration, they have two ways, either to lose 3 electrons or to gain 5. So they prefer to lose all the 3 electrons so that they acquire the previous period's noble gas configuration and they become stable. But what we find is boron, of course, we can't find boron in +3 state because it's all 3 ionization enthalpies are very, very high. But yes, with oxygen and other halides, it exists in +3 oxidation state. Whereas, yes, we get aluminium +3 in aqueous medium, and gallium, indium, thallium, they exist. But what we find, since the poor screening starts from the gallium or the 4th period, this we know from 4th period it starts, and in the 6th, 7th, particularly in the 6th period, this one, this is very, very worse. The reason being because of the because of lanthanide contraction, poor screening effect of the F electrons, F orbital electrons. What we find is in thallium, or in specifically in these 3 elements, as they have a D and the poor screening of the D continues, the NS electrons stop participating in the chemical reactions, or because of the high ionization enthalpies. As a result, in place of, along with +3, they also show +1 oxidation states. And though gallium's +3 is more stable than +1, indium's +3 is more stable than +1, thallium's +1 is more stable than +3. That is how the character changes, and this tendency to show the two different oxidation states with a difference of 2 is basically called inert pair effect because of the poor screening of the ns2 electrons by the inner f or d electrons. So that's the one peculiar thing we have, and that is what the change in the properties is. Another important thing is that we need to know this, since they have only 3 valence electrons, most of their compounds will be electron deficient. So they all will be Lewis acids. Whether they are halides or hydrides, whatever they are, they will be Lewis acids. And we know this, like if we talk about AlCl3, we know that it can't exist as such because its octet is not complete. So in solid state exists in the form of a dimer like this, where what we find is we have this kind of behavior. Like this is one AlCl3 unit, this is one AlCl3 unit, this chlorine gives one pair to this one, this chlorine gives one pair to this one, and this is how they both exist as dimers to Al2Cl6, they exist as dimers. So that makes their chemistry very much different from the rest of the elements. Another important thing is that since they doesn't have, even if we specifically, they are Lewis electron deficient compounds, they form Lewis electron deficient compounds, and particularly the boron is not having d orbitals. So boron in the form of boric acid accepts an OH minus ion, and it can go maximum of a 4 coordination number like this, whereas on the other hand the aluminium or any other one can accept OH minus ions like 3 in number, and they can go up to 6 with coordination number 6, and they therefore remains sp3 hybridized. They gets sp3d2 hybridized with octahedral geometry. So this is how their characters and their activities are very much different.